Here is a name you already know. You met it in school, bolted to the one piece of mathematics almost everyone carries out of the building and into the rest of their life. A squared plus b squared equals c squared. The Pythagorean theorem. It hangs on classroom walls. It has been proved, down the centuries, in more than 300 different ways, by schoolchildren, by Leonardo da Vinci, by a United States congressman who would later become president and worked out his own proof for fun between sessions of the House. If any equation has earned the right to be called famous, it is this one, and it wears a man's name across the front like a signature. And we know almost nothing about the man. Pythagoras of Samos wrote nothing down, or if he did, not a scrap survived. Everything we have about him was written by other people, most of them centuries after he died, and much of it is plainly the stuff of legend. He was said to have a thigh made of gold. He was said to be able to appear in 2 cities on the same day. He was said to remember all of his previous lives, to understand the speech of animals, to have been greeted by name by a river. He forbade his followers to eat beans, for reasons that no 2 ancient authors agree on. And one story, surely false, but too good to leave out, has him cornered and killed by his enemies, because he would sooner die than escape across a bean field. Strip away the miracles, and the golden thigh, and what is left is genuinely hard to pin down. We are not certain he proved the theorem that bears his name. We are not certain he proved anything. And we already know, from the last chapter, that the fact wrapped inside that theorem, the square on the long side of a right triangle equaling the sum of the squares on the other 2, was known and used in Babylon 1,000 years before Pythagoras drew breath, tabulated on clay while his ancestors were still illiterate. He did not discover it. Nobody who tells you otherwise is telling you history. So set the theorem aside for a moment, because the reason Pythagoras matters, the reason this chapter exists, is not a triangle. It is a vision of the entire universe, breathtaking in its ambition and beautiful in its simplicity, and the way that vision was destroyed by the very mathematics its followers held most sacred. This is the first great catastrophe in the history of the subject, and, like every catastrophe in this book, it turned out to be a beginning. Around 530 BC, Pythagoras left the island of Samos, off the coast of what is now Turkey, and sailed west to Croton, a Greek colony on the sole of the Italian boot. There he founded something for which we do not really have a modern word. It was not a school, the people learned there. It was not a monastery, though its members renounced private property and lived by strict rule. It was not a political party, though it seized control of the city and held it for a generation. It was all of these at once, a brotherhood, part research institute and part religion, bound together by secrecy and by a set of convictions that were, even by the standards of the ancient world, distinctly strange. They believed the soul was reborn after death, again and again, passing from body to body, and not only human bodies. The soul that animated you might once have worn feathers or fins. This is why they would not eat meat. The animal on the plate might be a relative, a friend, a former self, which makes it all the more suspicious that one legend has Pythagoras sacrificing 100 oxen in joy at proving his theorem, a vegetarian ordering the slaughter of 100 cattle. The story cannot be true, but it survived anyway, because a good story about a great man is one of the most durable things in the world, and one of the least reliable. They kept secrets. Knowledge inside the brotherhood was rationed by rank, and members were sworn not to reveal it to outsiders. And they divided themselves into 2 circles. The outer circle were the ekhausmatikoi, the listeners, who were given the conclusions, the rules, the sacred sayings, and were expected to accept them on the master's authority without asking why. The inner circle were the mathematikoi, the learners, who were admitted to the reasons behind the rules, the actual demonstrations, the working out. That second word is worth pausing on, because it is a gift the Pythagoreans handed across 25 centuries, and straight into the title of this book. Mathematikoi comes from the Greek mathema, meaning simply that which is learned. It is the direct ancestor of our word mathematics. Buried in the name of the subject is this ancient distinction between those who are handed an answer and told to believe it, and those who are shown why and allowed to see for themselves. Mathematics, from its christening, was supposed to be the second kind of knowledge, not take my word for it. Watch, I'll show you. And what the inner circle learned, above all, was a single staggering idea, that everything, literally everything, is number, not described by number, made of it. The Pythagoreans held that whole numbers, and their ratios, were not a human tool laid over the world, but the actual substance, and secret grammar of reality, and that if you could see deeply enough into anything at all, you would find, at the bottom, arithmetic. This sounds like mysticism, and in their hands it partly was. But you have to understand why they believed it. Because they were not simply making it up. They had evidence, real, physical, reproducible evidence. And it came from an unexpected place. It came from music. There is a story that Pythagoras discovered it by walking past a blacksmith's shop and noticing that some of the hammers, when they struck the anvil, rang out in harmony with each other while others clashed, and that the harmonious ones turned out to have weights in simple ratios. That story is charming and, unfortunately, false. The physics of a struck hammer does not work that neatly, and if you built the experiment it would not give you the result the legend promises. But there is a version of the discovery that is real, that you could reproduce this afternoon, and it is one of the most quietly astonishing facts a person can encounter. Take a taut string and pluck it. It sounds a note. Now stop the string exactly halfway along its length and pluck again. The note you hear is the same note, higher, what a musician calls an octave, the interval between a note and its twin at the top of the scale. The length ratio that produces it is exactly 2 to 1. Now stop the string so that you are plucking 2/3 of it. You get another beautiful, consonant interval, the one musicians call a perfect fifth, sitting at a ratio of 3 to 2. 3/4 of the string gives you a perfect fourth, at 4 to 3. Sit with what this means. The intervals that sound sweet to the human ear, the consonances, the combinations that have anchored music in every culture that has ever plucked a string are precisely the ones produced by the simplest whole number ratios. The ugly, jarring intervals correspond to complicated ratios. Beauty, in sound, is literally simple arithmetic. There is a hidden number inside the pleasure, and you can find it with a ruler. Now imagine you are a Pythagorean, and you have just discovered this. You have caught number red-handed, hiding underneath something. Sound, harmony, beauty itself, that seemed to have nothing whatever to do with counting. What would you conclude? You would conclude, as they did, that this is not a coincidence about strings. This is a clue about everything. If number secretly governs music, then perhaps number secretly governs it all, and the whole universe is, at bottom, a kind of instrument, playing chords we are too close to hear. They took that last thought literally. The planets and stars, they proposed, move through the heavens, at distances, and speeds set in whole number ratios, and in moving they sound tones, a vast, unheard cosmic harmony, the music of the spheres, which we cannot perceive only because we have been bathed in it since the moment of our birth, and have nothing silent to compare it to. It is one of the most beautiful ideas anyone has ever had about the sky. Kepler was still chasing it 2,000 years later. It is almost certainly wrong. It is also the kind of wrong that only a magnificent mind produces. To see how the whole edifice came crashing down, you have to see one more thing about how these people thought about number. Because it was not the way you and I think about it, and the difference is the entire drama. To a Pythagorean, numbers were not marks on a page. They were arrangements of things, of pebbles, of dots, of physical units you could pick up and lay out on the ground. And they had shapes. Lay out 1 pebble, then 3, then 6, then 10. And if you arrange each batch carefully, you get a growing series of perfect triangles. So these were the triangular numbers. Lay out 1, 4, 9, 16, and you get a growing series of perfect squares, the square numbers, which is exactly why we still call 4 times 4 4 squared. The names your teacher used are fossils of this ancient habit of seeing number as shape, and playing with the pebbles turned up marvels. Here is one the Pythagoreans loved. Start with a single pebble, 1. Add 3 more, arranged as an L shape wrapped around it, and you have a 2 by 2 square. 4. Add the next odd number, 5, wrapped around that, and you have a 3 by 3 square. 9. Add 7, 16. The pattern never breaks. Add up the odd numbers in order, 1, then 1 and 3, then 1 and 3 and 5, and at every step, without fail, you land exactly on a perfect square. You can see why, if you picture the L-shaped collars nesting one inside the next. That is not a rule someone handed you to memorize. It is a truth you can watch assemble itself out of stones. It is exactly the watch, I'll show you, that lived inside the word mathematics. Their most sacred figure of all was a triangle of 10 pebbles. 1, then 2, then 3, then 4, stacked into a perfect equilateral triangle. They called it the tetractys, and they held it holy enough to swear oaths upon. Look at why. The 4 rows contain the numbers 1, 2, 3, and 4. And those 4 numbers are exactly the ones whose ratios produce the musical harmonies. 1 to 2, the octave. 2 to 3, the fifth. 3 to 4, the fourth. The little pile of 10 stones contained, encoded in its rows, the harmony of the cosmos. To a Pythagorean, that was not a curiosity. That was a glimpse of the mind of God. But notice, and this is the hinge on which everything now turns, what this whole way of thinking quietly assumes. It assumes that everything is built out of whole units, indivisible pebbles, the counting numbers, and ratios between counting numbers, and nothing else, because there is nothing else to be made of. In this universe, any two lengths whatsoever can be compared as a ratio of whole numbers, because both lengths are ultimately just so many copies of some common little unit, some pebble small enough to fit a whole number of times into each. Take a fine enough measuring stick, and it will divide both lengths evenly, with nothing left over. The Greeks had a word for two lengths related this way. They called them commensurable, sharing a common measure. The Pythagoreans staked their entire worldview on the belief that all lengths are commensurable, that the whole numbers and their ratios are enough to measure anything, build anything, describe anything, that there are no gaps. And then one of their own found a gap. Bring back the theorem, their theorem, the one they may not have proved but certainly revered, and point it at the simplest shape imaginable. A square whose sides are each exactly 1 unit long. Draw the diagonal, corner to opposite corner. How long is it? The theorem answers instantly. The diagonal is the long side of a right triangle, whose 2 short sides are the edges of the square, each of length 1. So the square on the diagonal equals the square on one side plus the square on the other, 1 plus 1. 2. The diagonal is the length whose square is 2. The number we now write is the square root of 2. The square root of 2. Fine. So the Pythagorean asks the only question his entire philosophy permits him to ask. What whole number ratio is it? The diagonal and the side are both just lengths. They must be commensurable, like everything else. So there must be some fraction, some ratio of whole numbers, that gives the length of the diagonal in terms of the side. Find it, and you have measured the diagonal. That is all that measuring means. He never finds it. And then, this is the moment the ancient world tips on its axis. He proves that he never can. Not because he isn't clever enough, because no such ratio exists, and it is possible to prove, with total certainty, that none ever will. Let me show you the proof, because it is short, it is airtight, and it is one of the most consequential arguments any human being has ever constructed. It is also a new kind of argument, a weapon the Pythagoreans and their successors were just learning to forge, and once you have watched it work, you have understood something about mathematics that separates it from every other form of human knowledge. The trick is this: you begin by assuming the exact opposite of what you want to prove, and then you follow that assumption, with perfect obedience, until it destroys itself. So, suppose the diagonal and the side are commensurable. Then the ratio of the diagonal to the side can be written as a fraction. Call it a top number over a bottom number, both whole. And here is the one preparation we need, whatever that fraction is. We insist on writing it in lowest terms. That is, we cancel any common factor. If both numbers were even, we would divide both by 2, and keep going until we couldn't anymore. Every fraction can be reduced this way. 3/6 is really 1/2, so this costs us nothing. We simply agree that our top and bottom numbers share no common factor. In particular, they are not both even, because if they were, we would have cancelled that share too. Hold on to that. Not both even. Everything hangs on it. Now the machinery. The length whose square is 2. That is what our fraction equals. So the fraction, multiplied by itself, must give 2, which means the top number times itself equals twice the bottom number times itself. And the instant you write that down, you have learned something. The top number, squared, is 2 times something. So the top number, squared, is even. But if a number squared is even, the number itself must be even. Think about it for a second. An odd number times an odd number is always odd. 3 times 3 is 9. 5 times 5 is 25. The odd stubbornly survives. So the only way to square something and land on an even number is to have started with an even number. So our top number is even, which means we can write it as 2 times something. And if you substitute that back into the relationship, the top squared equals twice the bottom squared, and grind through the little bit of arithmetic, the same conclusion falls out about the number on the bottom. It, too, must be even, and there is the detonation. We have just shown that the top number is even, and the bottom number is even, that they are both divisible by 2. But we began by insisting, without any loss, that they share no common factor. They cannot be both even and share no common factor. It is a flat contradiction, the mathematical equivalent of proving that a bachelor is married, something we assumed must be false. We were careful about every step but one, the very first, where we supposed that the diagonal and the side were commensurable in the first place. That is the assumption that blows up. And so it is not true. The diagonal of a square cannot be expressed as any ratio of whole numbers to its side. Not a big ratio, not an ugly ratio, not a ratio nobody has found yet. No ratio at all, forever, and here is the proof. This is not a modern reconstruction dressed up in old clothes, by the way. Aristotle, writing in the 4th century BCE, refers to exactly this argument, the incommensurability of a square's diagonal, established by showing that odd numbers would have to equal even ones. The reasoning you just followed is, in its bones, more than 2,000 years old. Now feel what it did to them. The Pythagoreans had built a universe out of whole numbers and their ratios. They had staked everything on the conviction that number, in this narrow and beautiful sense, was enough to measure any length, to capture any quantity, to underwrite the whole fabric of the cosmos. And here, sitting inside the most elementary figure in geometry, drawable by any child in 2 seconds, was a length that their numbers could not touch. The diagonal was real. You could see it, draw it, cut a stick to its size, and it slipped clean through the net of every fraction there is. There was a hole in reality, and it was shaped like the most obvious line you could draw across a square. The Greeks reached for a word, and the word they found tells you how the discovery felt from the inside. A length like this, they said, was alogos. And logos is one of the great load-bearing words of the Greek language. It means ratio. But it also means word and reason and account, the very same root that gives us logic. So alogos meant, at the same moment and in the same breath, without ratio and unspeakable, and that of which no rational account can be given. The number was, quite literally, unutterable. A thing reason could not say. We have inherited that word, worn down by translation. We call such numbers irrational. And if you have ever wondered why a perfectly well-behaved quantity, like the square root of 2, should be tarred with a word that everywhere else means unreasonable, deranged, not to be listened to, now you know. It is a fossil of the shock. The name still carries, 25 centuries later, the faint horror of the people who first met the thing, and found that it could not be spoken. And there is a final, exquisite twist of the knife, the secret badge of the Pythagorean brotherhood, the sign by which one member recognized another, the emblem they associated with health and wholeness, was the 5-pointed star, the pentagram. It turns out that if you take the humble 5-pointed star, and ask how its lines divide one another, you find, threaded through it, another incommensurable ratio, the one later ages would christen the golden ratio, every bit as unspeakable as the diagonal of the square. The disease was not off in some exotic corner of geometry. It was hiding inside the very star they wore over their hearts. Which brings us, at last, to the story this book opened with. Tradition gives the discovery of incommensurability to a man named Hippasus of Metapontum, a member of the Brotherhood, and tradition says that for revealing it, he drowned. In some versions, his fellow Pythagoreans, unable to bear that their sacred worldview had been broken from within, threw him from a ship into the sea. In others, the gods themselves drowned him, infuriated as having let an unspeakable thing be spoken aloud. The versions contradict each other. The sources are late and unreliable, and no serious historian will tell you it happened as described. It is, almost certainly, a legend, but I want to be careful about what a legend means here, because it is not the same as a lie. A legend is a story a community tells to hold on to something it could not otherwise carry, and what this one holds onto is real, whatever the facts of any actual drowning. It records a trauma. It preserves the memory that this discovery landed not as an interesting result, but as a scandal, a dangerous, forbidden, world-breaking thing, so threatening to the people who found it that the story of its finding got told, ever after, as a death. You do not invent a drowning to remember a minor technical footnote. You invent it to remember an earthquake. The legend is false, and the earthquake is true, and the legend exists precisely because the earthquake was true. That is worth remembering every time we meet one of these tales, and we have met a few already: the rope with its 12 knots, the 100 slaughtered oxen. The deep past hands us silhouettes and blurs, and the honest historian learns to say probably, and we cannot be sure, but the silhouette is still the shadow of something that stood there. Underneath the legend of Hippasus is a genuine intellectual catastrophe, and it genuinely changed the course of mathematics. Here is how it changed it, and this is the real payoff of the whole chapter, the thing that echoes for the next 1,000 years. Number had betrayed the Greeks. The counting numbers and their ratios, which the Pythagoreans had trusted to measure the whole world, had proven unable to measure a line you could draw in the dust. So Greek mathematics did something momentous. It stopped trusting number, and turned instead to geometry, to lengths, and shapes, and areas, the continuous, drawable, spatial things, which had no such embarrassing gap. You cannot express the diagonal as a fraction, true, but you can draw it exactly, with a straight edge and compass, no trouble at all. The geometry was solid, where the arithmetic had cracked. So the Greeks made geometry the bedrock, and demoted number to something you approach through shape. This single decision is why, when you open the greatest mathematics book of the ancient world, which we are about to do, you find its author proving what look like facts about numbers and equations entirely through pictures of lines and rectangles, never quite trusting a formula, always insisting on a figure you can see. It looks strange to a modern eye, almost perverse. Why do all this geometry to say something about numbers? The answer is the scandal of the diagonal. The Greeks had learned, the hard way, that their numbers had holes in them, and their shapes did not, and they built the most durable structure in the history of thought on the ground they had found to be solid. The monster drove them toward the foundation, and the monster itself, the square root of 2, the unspeakable length, the number reason could not say, the discovery worth telling as a drowning, is, today, a button on a calculator. Every teenager on Earth summons it without a flicker of unease, reads off its endless unrepeating digits, uses it to find the diagonal of a screen, or the reach of a ladder, and thinks nothing of it at all. The thing that shattered a philosophy and, in legend, cost a man his life is now so ordinary that it is boring. We hand it to children. That is the pattern this book is named for, and here is its very first turn. A forbidden object, an impossible length, a number that could not exist inside the accepted universe, arrives as a catastrophe, gets a fearful name, breaks a worldview, and is then, over the slow centuries, tamed, absorbed, made routine, until nobody can remember what the terror was about. The impossible made ordinary. It will happen again with zero, and with negative numbers, and with the imaginary, and with infinity itself, and each time it will feel, to the people living through it, exactly as final and exactly as scandalous as it felt to the brotherhood at Croton. But before any of those, there is a man in Alexandria, who is about to take the wounded, geometry first mathematics the diagonal left behind, gather up a handful of assumptions so simple they seem to say nothing at all, and build from them, step by careful step, proving every inch, a fortress of reasoning that will stand, essentially unchallenged, for more than 2,000 years, longer than any empire, longer than any religion's settled form, longer than almost anything human beings have ever made. His name was Euclid, and his machine is next.